Um, well, it's a great pleasure to have Professor Nathan Wagner from George Mason University. So he will give us a talk today on commutators and paraproducts in the non-homogeneous setting. Thank you, Nathan.
Thank you, Ziming, and thank you very much for the kind invitation. It's nice to speak in this seminar. If anybody has a question while I'm going through this talk, please feel free to just say something because I may or may not see like the raised hands. But feel free to stop me if something's not clear. And what I'm going to talk about today is joint work with Francesco D'Emilio, Yongxi Lin, and Brett Wick at Washington University in St. Louis. And this talk will very much be about dyadic harmonic analysis, although there are some motivations from other areas of harmonic analysis. So the rough plan for the lecture is we'll talk about the basic objects of study being functions in BMO or of bounded mean oscillation. Talk a little bit about dyadic grids and operators, as well as paraproducts and commutators, which are the specific operators that we're studying. Then I'll tell you what our main results are. And then in the third section, if I have time, I'll dig in a little bit more into some of the ideas behind the weighted inequalities that we prove. Okay, so the story starts here. Just in the simplest possible case, we think about the Hilbert transform defined on Schwartz functions or convolution by 1 over x. It's given by this principal value integral. And many of you are in harmonic analysis, so you know that this is the prototypical example of what's called a Calderon-Zygmunt operator, meaning it's an integral operator, a singular integral operator that is given by integration against some singular kernel function, and that kernel has to satisfy size and smoothness estimates for the operator to have good properties. And we also usually assume that it's bounded on L2 to get started, and the Hilbert transform satisfies all of those things. Not only is it bounded on L2, and you can see that just from computing the Fourier transform and looking at its symbol, which it just is negative I sine of C. It's also bounded on LP for P strictly between 1 and infinity. So it preserves the Lebesgue spaces in the reflexive range. But the endpoint estimates fail. And the upper endpoint estimate when P equals infinity, it's well known that H doesn't map L infinity to other bounded functions, but rather maps L infinity to a slightly larger space. And that's the BMO space that we're going to introduce on the next slide. And so this is the definition of BMO. These are functions of what's known as bounded mean oscillation. And the name really gives the definition of these functions because their oscillation, which is measured by taking the function minus its integral average. So here the notation bracket b on I means integral of b over I divided by the Lebesgue measure of I. The modulus of that difference, if we average it to compute the mean oscillation on an interval I, how much the function is deviating from its average, that quantity remains bounded as we take a supremum over all intervals. And okay, the importance of this space, well, it's important for many reasons. One is that I told you that it sort of as this endpoint counterpart to L infinity, but it also characterizes the operator norm of commutators. So if I think about the commutator of the Hilbert transform with multiplication by b, which is a very simple operator, you just multiply by b. You can think of that as an operator on your Banach space that will be bounded in circumstances, or at least densely defined. And you want to measure how much the Hilbert transform commutes with multiplication by b. So you look at the commutator h applied to bf minus b times Hilbert transform of f. The idea here is that there's some cancellation in this commutator. It isn't identically zero, right? If b is, say, a constant function, it's zero. But for more general functions, there's suitable cancellation in the difference that lets you extend the commutator to a bounded operator on LP. And this happens if and only if the symbol of the commutator, which is called b, which is also the symbol of the multiplication operator, belongs to BMO. And there's sort of a better behavior that arises from considering the commutator than multiplication by b alone, because if you take multiplication by b just by itself, you would need the function to be L infinity. But for the commutator, we're able to leverage the cancellation to prove this for a slightly larger space. And the beautiful theorem says that we can not only get that characterization, but we can also have an equivalent renorming of BMO in terms of the LP norm of this operator, right? The BMO norm is comparable to the LP norm of the commutator. And really the key idea here is that commutators with special singular integral operators can be used to characterize BMO. And there's various generalizations of this result to more general settings. Okay, I'm going to move now from sort of the continuous to the dyadic world. I'm going to talk about dyadic grids in a second, but we can define a dyadic BMO space by considering the supremum only over dyadic intervals rather than all intervals in the BMO norm. And some motivation of doing this is there's kind of this well-known trick called the 1/3 trick that allows you to take a dyadic grid and sort of shift it by an amount that's badly approximable by dyadic numbers. And then you have two dyadic grids, and you can actually take the intersection of those two dyadic BMO spaces to recover the continuous BMO space. There's a paper, for example, of Tao Mei that does this. Now, just as in the continuous case, we have a characterization of BMO via the commutator with some operator, in that case, the Hilbert transform or Riesz transforms. Petermiko and collaborators recently observed that if you take some sort of toy model dyadic version of the Hilbert transform, which we're denoting by script H, this operator is bounded on L2 if and only if B belongs to dyadic BMO. And they actually proved more because they proved it in the biparameter setting and for BMO with dyadic rectangles. But in the one parameter setting, it collapses to this. And basically, if you assume that your measure is dyadically doubling, your underlying measure for the space, and so that means that there exists some constant so that the mu measure of the dyadic parent of a dyadic interval I is controlled by that universal constant times mu of I, then the theory is basically the same as for the classical case. You can define a dyadic Hilbert transform with respect to mu by taking Haar functions that are orthogonal in L2 mu, and you'll still get this nice, clean characterization of the dyadic BMO norm in terms of the operator norm of this commutator. So we were interested in the case when, of course, the underlying Borel measure is not dyadically doubling, and that's what I want to get into next, and that's what it says in this blue text here. What happens in the non-homogeneous setting? Okay, so I think everyone's probably familiar with the construction of the standard dyadic grid on the real line. You take all intervals of the form 2 to the negative k times the interval m to m plus 1. If you think about all the dyadic intervals in 0, 1, you start with 0, 1, you cut it in half, Then you cut the two resulting children intervals in half, and then you continue that procedure, right? And just some notation and pictures. So if we have like a dyadic interval I, which is shown here in blue, the dyadic sibling of it is denoted. Sorry, is there a question? I hear some weird echo thing, so maybe it was just that. Can't see the video bar. Okay. So the dyadic sibling is this orange interval IS. Their dyadic parent, which has length twice the length of I, is shown in the gray interval, and that's denoted by I hat. And then we'll denote the two dyadic children of the blue interval I by I minus and I plus, obtained by dividing the interval in two, and that's the pink interval and the green interval here in the slide, and denoted I minus and I plus, respectively. Okay, so this is just some notation. And we're going to look at the following model operator that is useful because it can characterize dyadic BMO in the way that the continuous classical Hilbert transform characterizes BMO. And this function, or this operator H, applied to F, maps to the following Haar series. So it's a priori defined for F and L2. And you notice that it's characterized by its action on Haar functions HI. So here HI is just the Haar function or Haar wavelet on I. And we see that H of I plus maps to the Haar function HI minus, so that it maps I plus to its dyadic sibling, the Haar function of its dyadic sibling, and it maps HI minus to minus HI plus. So a compact way of writing that would be H of HI is equal to the sine of I times HI sibling. And this operator is a good model for several different reasons for the continuous Hilbert transform. One reason is that H squared is equal to minus identity. Okay, so you have this like anti-self-adjoint property. And there's sort of square wave analogs of the fact that the Hilbert transform maps cosine to sine and sine to negative cosine, right? And so if you compute what this operator does on Haar functions, you'll see that this comes up. And it's also connected to some proofs of matrix-weighted inequalities for the continuous Hilbert transform. And this showed up in some recent work of Trail. So there's many reasons why this operator is kind of an interesting operator. And we already said that it can be used to characterize BMO. Okay, so now I'm going to move to higher dimensions. So that was some one-dimensional motivation. But in Rn, we can also, of course, consider dyadic systems, and we can build them by taking Cartesian products of equal length dyadic intervals to generate dyadic cubes. And then we just take some Borel measure mu on Rn that's locally finite in the non-zero on each dyadic cube. And we can define some operators that are relevant in martingale theory and probability. So conditional expectation just means that we average f on the dyadic cube q and multiply by the characteristic function of q. And here the integral averaging is done with respect to the underlying measure mu. We can also look at the martingale difference operator, delta q applied to f, which is obtained by summing over the dyadic children of q, which we label r, expectation on r of f minus expectation on q of f, and it can be rewritten in the second way as well. And if you think about just the one-dimensional case, delta q is going to be the projection of f onto the one-dimensional space that's spanned by the Haar function hq, right? So these are objects which show up very naturally when we move to higher dimensions. And again, we're going to use the notation q hat to denote the dyadic parent of the cube q. in this higher dimensional setting. Okay, there are kind of competing definitions of dyadic BMO when your measure mu is no longer homogeneous, no longer dyadically doubling. So this first definition you might call martingale BMO, and it's defined using the following norm, and denoted by BMO P mu. It's almost the same as the usual dyadic BMO norm that I showed you in the one-dimensional case, but instead of subtracting off the average of B on Q itself, we subtract off the average of B on the dyadic parent Q hat of Q. And that turns out to make a difference when the measure mu is not a dyadically doubling measure. Conversely, we can define these little BMO spaces, which is denoted by a lowercase BMO, P, if this more classical looking dyadic BMO condition is satisfied. So there we just subtract by the average of B on Q. We don't subtract by the average on the dyadic parent. And you can use the orthogonality of the martingale differences to easily calculate when P equals 2, this is equivalent to kind of what's known as this Carleson packing norm or Carleson norm of a BMO function, where you sum up the L2 norm of delta RB, where R is a dyadic descendant of Q, and then you divide by mu of Q and take that to the 1/2. That ends up being the same thing as when in this integral above, you replace P with 2. And again, you can see that just using orthogonality. These spaces have some interesting properties in the non-homogeneous setting that don't show up with, say, Lebesgue measure or even doubling measures. First, there's a variant of the John-Nirenberg inequality in this martingale setting that tells you that these spaces BMOP, the ones that were defined using the dyadic parent instead of the dyadic cube itself, these are independent of P with equivalent norms. Okay? The same is not true for the little BMO spaces. Those depend on P, and in fact, when mu is not doubling, there's a strict containment of big BMO in this little BMO. Okay? If mu is doubling, then all the spaces coincide, so it's sort of not very interesting. As I said before, in general, the spaces BMOP, these Carleson norm spaces, are P dependent, and we get the nesting that's expected, and you just get that nesting from an application of Holder's inequalities. So there's sort of, you see immediately which way the nesting should go. The spaces become smaller as you increase the exponent, just by Holder. Okay, so there's some interesting behavior that happens here that we're not seeing in the classical case. That's kind of the point of this. Okay, we now want to define some important dyadic operators in the higher dimensional setting, which arise from considering commutators, kind of pieces of commutators. So the idea is, if you look at a product of two functions B and F, you can kind of do a martingale expansion on both of them and then look at pieces of that martingale expansion. And so one such piece is what's called a paraproduct or partial product. It's denoted by a pi b, and this operator takes the expectation on Q of F times the martingale difference delta QB and sums it up over all dyadic cubes. There's also the L2 adjoint of a paraproduct operator, which you can just directly compute using duality, and you get this formula. There's also sort of this diagonal operator delta B, where you have a sum of martingale difference delta QB times delta QF. This operator, if your underlying measure is Lebesgue, it will be the same as the L2 adjoint of the paraproduct, but for general measures, this is a different operator. And there are two more related operators. One is this lambda B0 operator, which basically you get by taking the paraproduct pi b and you applied to F and you interchange the roles of B and F. Okay, so now the expectation is on B and the martingale difference is on F. And then there's a variant of this, which is denoted by lambda B, and it has this formula. And so these are just some operators that are going to play a role in different decompositions that we're going to apply to commutators later. Okay, before I state our results, I want to briefly review what is a sparse collection. So this is occupied a lot of work recently in harmonic analysis. The idea is you're looking at some collection of dyadic cubes that aren't necessarily all disjoint, but they're sort of almost disjoint, and they have a relatively small amount of overlap. So if we fix our parameter eta in 0, 1, a collection of dyadic cubes is said to be eta sparse. If for each q in the collection, each dyadic cube q, we can find some measurable subset EQ that satisfies this inequality, mu of EQ is greater than or equal to eta mu of Q. So EQ takes up at least some fixed portion of the mu measure of Q. And the Q's themselves may not be pairwise disjoint, but if you pass to this collection of subsets that have sort of large measures relative to Q, then that collection is pairwise disjoint. So they sort of have big pairwise disjoint pieces. There's this equivalent condition which holds as long as the measure mu is atomless, and it's a so-called Carleson packing condition. And what do we do there? Well, we stipulate that there's some constant lambda greater than 0, so that when you sum up all dyadic cubes belonging to the sparse collection contained in Q, mu of R, then you get at most a constant times mu of Q. Of course, if all the cubes in the sparse collection were pairwise disjoint, right, then you would just be able to bound this by mu of Q. You wouldn't need a constant there. Okay, so that's what we mean by a sparse collection. And the utility of the sparse collection is what's called sparse domination. And that involves taking an operator that's usually something like a Calder-Zygmunt operator, or a Haar-Shift, a paraproduct, or some other type of operator in harmonic analysis. And typically it's an operator that's going to be well-defined, say, on bounded compactly supported functions, and maybe it has a bounded extension to L2. And then if it's Calder-Zygmunt, then you also get its bounded in LP. But the point is that we're actually able to control this operator pointwise by sort of this very simple positive dyadic averaging operator. So I'm summing over finitely many dyadic grids from L equals 1 to n. That's sort of not a big deal. But for each fixed dyadic grid, this is a very simple dyadic averaging operator, which looks almost like a conditional expectation, right? I'm summing over a collection of dyadic cubes, average of F on Q times the characteristic function of Q. And of course, the cubes in this collection are sparse. They're, as we defined in the previous slides, so they're not necessarily pairwise disjoint, but they're close enough to being disjoint that we can sort of get good control on them. And this enables one to do a lot of things. For example, prove sharp weighted inequalities, prove weak type estimates. There's myriad applications of sparse domination. So we want to examine commutators and paraproducts in the non-homogeneous setting. Lacey, back in one of his famous early sparse papers, did obtain sparse domination for paraproducts in the non-homogeneous setting, but he assumed a stronger packing condition on the BMO symbol. And I'll mention that slightly on a little bit on the next slide. There was also work of Frag-Kiadaki and Holmes-Fay. They looked at kind of a Bloom-weighted sparse domination for dyadic paraproducts, but the underlying measure was still Euclidean, so they weren't in the non-homogeneous setting. Trail did some interesting work on paraproducts and commutators with martingale transforms in the non-homogeneous setting. So he characterized when the paraproducts pi b are bounded on LP mu, and sort of surprisingly, it's not just martingale BMO. It's something that depends on p. And he also constructed some sort of interesting examples and counterexamples. Bonamy looked further at this kind of stuff with endpoint estimates in the non-homogeneous martingale setting. And I previously did some work with Tainara Borges, Jose Conde Alonso, and Gilles Pipher, where we looked at this model operator H, this dyadic Hilbert transform that I told you about earlier. So that's just in dimension 1. And we looked at the commutator with that dyadic shift operator, and we proved some upper and lower estimates in terms of BMO norms. And a surprising result that we found, a kind of a novelty in the non-homogeneous setting, is that you can't use LP norm inequalities with the commutator of B with this dyadic Hilbert transform H to characterize martingale BMO. So that characterization of martingale BMO fails when your measure is no longer dyadically doubling. And that was kind of our jumping off point for this present work. Okay, let me tell you a little bit about this packing condition that Lacey assumed that was stronger than sort of it needed to be. So Lacey wanted to obtain sparse domination for dyadic paraproducts for general radon measures. I think he also did something with martingale transforms and such in the same paper. But this is the packing condition that he imposed. And if you remember the usual Carleson packing condition, you don't have an L infinity norm on delta R B squared times mu of R. You have just an L2 norm squared. But just by Hölder's inequality, you get that this L2 norm squared is controlled by the infinity norm squared times mu of R's, right? So that's trivial. And so this implies condition 1 is stronger. It implies the Carleson packing condition. And you can actually show that it also implies the martingale BMO condition, which is stronger than Carleson packing. But we were able to give an explicit example of a non-doubling measure mu and a symbol B in martingale BMO that fails this trail packing. Okay, and that ties into sort of our first contribution here. So this is theorem A. And basically what this does is this achieves sparse domination for dyadic paraproducts, as well as the adjoint of the dyadic paraproduct in this other operator, delta B. In the non-homogeneous setting, it's a very general setting. It's just a radon measure mu satisfying this condition. And we get sort of the classical sparse domination with only the assumption that B is in martingale BMO. And so that's strictly weaker than what Lacey assumed. And of course, once we have the sparse domination, we can sort of run known machinery to prove weighted inequalities, right? So below, I have an estimate on the operator norm on weighted LPW of T, in terms of the dyadic AP weight characteristic. And this is sort of the sharp power that you expect from sparse dominations. It's the same as the sharp power for Calderon-Zingman operators. I'll talk more about weighted inequalities a little later, but the big idea is we get sparse domination in this case. There's some corollary to this whose statement looks kind of complicated, and I'm going to unpack it later. In the non-homogeneous setting, it was previously known that weighted inequalities, the usual weighted inequalities in sparse domination fail for like Haar shifts, for example. So Haar shifts of complexity 1 or greater, you can't achieve the usual sparse domination or weighted inequalities. There is a replacement weight class where you assume more on the weight. And we're able to actually prove weighted estimates on the commutator of a Haar shift, in this case, the dyadic Hilbert transform with B. And this condition, which I haven't defined it yet, I will if I have time on later slides. This condition that W belongs to this AP sibling class, it's a strictly weaker assumption than one that we assumed in a previous paper, which was that W belongs to AP hat. So that was what was previously known. So we improved this result qualitatively. We got sharpened weighted inequalities. And actually, there's more general results we have for generic Haar shift T in higher dimensions. But I'm just going to talk about the one-dimensional case and the dyadic Hilbert transform for the simplicity of presentation. Okay. Another thing that we were able to do is characterize when this commutator HB is bounded. So I told you before that martingale BMO cannot be characterized by the operator norm of this commutator in the non-homogeneous setting. So there's actually some replacement condition, which we denote by bracket BMOP or commutator BMO, which is strictly sandwiched in between martingale BMO and this little BMOP, which is like the Carleson packing BMO. And we have an explicit example of a measure for which both these containments are strict. And this class, bracket BMOP, it's defined in a somewhat funny way. The first condition says that it belongs to little BMO alpha P, where alpha P is the maximum of P and P prime, where P prime is the Holder conjugate to P. And then the second condition is that a certain sequence beta Q belongs to little L infinity. So it's a bounded sequence. And the way the sequence is generated, beta Q is defined as CQ minus CQ sibling. So here we're in one dimension. So every dyadic interval is a dyadic cube and it has a unique sibling. And CQ is this following inner product, B with HQ squared. Now, if this was just the Euclidean setting, HQ squared, the inner product with that would just give you the average of B and Q. But in the non-homogeneous setting, the Haar functions are defined to be orthogonal on L2 mu. And so HQ squared is actually something more complicated than just 1 over the measure of Q times the characteristic function of Q. So this is a somewhat weird condition, but it reflects the action of the operator, that this operator sort of interchanges dyadic siblings. And this characterization completely characterizes when this commutator is bounded at LP. So what are the ingredients that go into this? I don't have time to tell you about all of the details, but I can tell you about a few. So for the sparse domination, like many sparse domination proofs, you need some kind of weak type estimate to run the stopping time argument. So what we do is we look at a maximal truncation, which is denoted by pi b sharp, of the paraproduct pi b. And basically, it's kind of taking these cutoffs or truncations of the paraproduct, right? We're only summing over Q dyadic cubes contained in Q naught. Taking the absolute value and taking a supremum over all Q naught containing the point X. So this is some sort of maximal truncation operator. And we need to prove a weak type estimate for it. To get this weak type estimate, we use a modified Calderon-Zygmunt decomposition that works well in this non-dyadically doubling setting. And I think this version is originally due to Jose Conde Alonso, but it simplifies an earlier idea of Lopez, Sanchez, Martel, and Parset. And it proceeds as follows. Like a regular Calder-Zygmunt decomposition, you write F as G plus B, that's good plus bad, but your bad function is defined a bit differently. In the classical case, you would do a stopping time, so you would select dyadic cubes Qj that are the maximal dyadic cubes, so that the average of F on Qj is bigger than lambda, right? Or the average of the absolute value of F is bigger than lambda. We select the stopping intervals in the same way, the stopping cubes, but instead of subtracting off F minus its average of Q, we subtract off its average on Q hat, the dyadic parent. You see this kind of echoes the way that we defined martingale BMO previously in this talk. And it turns out that this decomposition, so now the bad functions are they're actually supported on Qj hat, and they have mean value 0 on Qj hat. But this decomposition turns out to be the right one to be able to prove like weak type estimates. And if you apply this different Calder-Zygmunt decomposition that's sort of adapted to this non-homogeneous case, then you can prove the weak type estimate for the maximal truncation, and then you win. Because then you can follow a more or less standard stopping time procedure to achieve the pointwise domination, and you use the weak type estimate to control the measure of the cubes you select, and that means that you can ultimately establish the sparse condition, or the Carleson packing sparse condition. Oh, sorry about that. Okay, so on the other hand, for the weighted inequalities, I'll explain this more in the next section, but the big idea here is that we're able to iterate weighted estimates. So we can do a decomposition of the commutator into the commutator of a paraproduct plus commutators with these other dyadic operators, delta B and lambda B0. And then we can, for each of these commutators that we've split the commutator on the left-hand side into, we can iterate weighted estimates. So for example, pi b has certain weighted estimates that come from it having sparse domination. The operator h is also known to satisfy certain non-standard weighted estimates. That's where this A2 sibling class comes in. And so I can peel off in turn the operator h and the operator pi b, for example, to get weighted inequalities for the commutator. And I'll explain more on this later. But the idea is that you do some sort of iteration with this paraproduct decomposition of the commutator to get the better weighted estimates. And the quantitative sharpness of all of these constants is still very much open. To get the LP characterization, we use a slightly different splitting of, that's a typo. It should be the commutator, not the paraproduct. But we split the commutator into these three pieces. We have the commutator with the paraproduct pi b, and the commutator for the adjoint of the paraproduct pi b star. The commutator of h with pi b, it's known that the paraproduct pi b is bounded if and only if b belongs to little BMO p. And that was a characterization that was actually provided by Trail in that paper I told you about earlier. And so if I want both this operator and this dual operator where pi b is replaced by pi b star, if I want both to be bounded, that's why I need b to belong to BMO alpha p, where alpha p is a max of p and p prime, right? So there's a duality thing going on. Moreover, you can do a direct calculation that establishes the commutator norm is controlled from below by this little BMOP norm. And so once you know the commutator is bounded, B has to belong to little BMOP, and we get the control on little BMOP prime by duality, because the commutator is essentially a self-dual object if you take its L2 adjoint. And then we've dealt with these first two pieces, right, in the decomposition, but we have to deal with the third piece. And this piece, you do a calculation, and you see that it's actually a Haar shift with coefficients equal to this beta Q quantity, which is the difference of these inner products, which is, again, this kind of funny condition that involves B inner product with HQ squared. And this operator is going to be bounded if and only if the sequence of coefficients is in little L infinity. And so by splitting this into pieces with this particular paraproduct decomposition, we can completely characterize the LP bounds. And I just wanted to emphasize again that we have examples showing that all of these inclusions are strict. And you can even do this when the underlying measure mu is absolutely continuous with respect to the Lebesgue measure. Okay. I think I have about 10 minutes left or so. So I want to tell you a little bit more about how things go in this dimension one case. So the way that you define all of these dyadic shifts and dyadic Hilbert transform and so on is you need an orthonormal basis of Haar functions for L2 mu. And in fact, in one dimension, if you want to take functions which have mean value 0, are constant on the dyadic children of I, is supported on I, and has L2 norm 1, up to a sign you basically only have one choice of the normalization. So the normalization that's correct, rather than 1 over the square root of the Lebesgue measure of I times characteristic of the left minus characteristic of the right, that's what you would do in the Lebesgue case. But in this non-homogeneous case, you have some weighted version of that, right? So this quantity m of I shows up as a normalization factor, and hi is square root of m of I times the difference of these characteristic functions divided by the measures of the two children intervals. And this m of I quantity, if you just compute what the normalization is, you get that it's equal to the product of the mu measures of the two children intervals, mu of I minus times mu of I plus, divided by mu of I. And a moment's thought will convince you that this is comparable to the minimum mu measure of the two children. And all of these inner products, for example, are with respect to the measure mu. And the first basic question that was looked at in a previous paper is, when is this operator H bounded? Well, it's bounded automatically in L2 mu by orthonormality of Haar functions. But it's not necessarily bounded in LP mu. And it turns out that the condition for this operator to be bounded in LP mu is this sibling balance condition, which is something strictly weaker than dyadic doubling. And it says that m of I is comparable to m of IS for all dyadic intervals I. And recall that IS is the dyadic sibling of I. And this is not saying that the measure of mu is comparable to the measure of the sibling interval, because this quantity m, it's equal to the minimum of the measures of the two children. And in general, that could be much smaller than the measure of the interval. And the importance of this condition is that it's both necessary and sufficient for the operator H to be bounded in LP mu when P is different from 2. Okay, so in this non-homogeneous dyadic world, we had previously looked at this class AP hat. We studied this in a previous paper. And it's defined the same way that the usual AP condition is defined, except you have two averages, one of the weight and one of the sort of the dual weight, right? And those averages don't have to be over the same dyadic interval, but they're either the same or one is a dyadic parent of the other. And so this is a stronger condition than just ordinary dyadic AP when mu is not dyadically doubling. And so what we showed is there's some nice features that motivate the study of this class. And one is that if W is an A2 hat weight, then log W belongs to martingale BMO. Moreover, if B belongs to martingale BMO, there exists some small number delta so that e to the delta B belongs to A2 hat. So it's the right space of weights to characterize martingale BMO. And it satisfies a dyadic reverse Helder inequality, which is something that isn't general true for dyadic AP weights. So it has some nice properties. And this was the class that we had previously proved weighted estimates for. But it turns out that we were able to improve that. So to discuss this, we need to look at some modified sparse forms that arise when considering this Hilbert transform operator. And these modified forms sort of arise because you can be in a situation where you have two intervals, dyadic intervals, say Q and R, that are dyadic relatives of each other, so they have some common dyadic ancestor. But because the measure is not dyadically doubling, there's no good way to compare their mu measures. And so this first sort of funny looking sparse form, I have an average of F on Q, that's usual. But instead of multiplying by the characteristic function of Q, I multiply by the characteristic function of R, where R is some dyadic relative of Q, also in the sparse collection. And in this case, Q hat is equal to the sibling of R hat. So I guess this means that these intervals, they're sort of like dyadic cousins. And we also have this normalization factor, m of Q hat to the 1/2, m of R to the 1/2 divided by mu of R. And there's sort of this other one that comes up where instead the relation is Q is equal to R hat S. And so in this case, one interval is like kind of like the dyadic uncle or the dyadic aunt, if you prefer, of the other interval. So there are these configurations that arise, and it turns out if you add those on to the ordinary sparse form, you can achieve sparse domination of this dyadic Hilbert transform. And that was actually, it was known before. And it's also known that the classical sparse domination fails. So if you just try to put AS, it won't work. Okay, so the result is, in a sense, sharp. And there's also this natural weight class that comes out of the sparse form, that comes out of the configuration of the sparse form. And this is this AP sibling class. And is exactly the class of weights for which the sparse form will enjoy weighted LP estimates. And so the sibling class is defined in this way. But again, what I want you to notice is that it involves averaging W over R and then averaging the dual weight W to the 1 minus P prime on some other dyadic cube or interval R, which is dyadically related, right? So that's kind of captured in this definition of the CPQR constant, right? So it's 1 if Q equals R. It's some normalizing factor if Q and R are in the positions that we discussed about. These are exactly the conditions that show up in the configurations that show up in the sparse form, and then we set the constant equal to 0 for all other cases. So usually this is 0, but if Q and R are sort of in some special conditions, then it won't be 0. And the important thing here is that there exists a non-doubling Borel measure mu, so that A2 hat is strictly contained in A2 sib. And so basically what we were able to do is previously in a previous paper, we assumed this AP hat condition, and that was sufficient to get commutator weighted estimates. But in our current work, we proved that the strictly weaker condition, W is an AP sib, is sufficient to guarantee that it's bound, that the commutator is bounded on LPW. it was previously shown that this weaker condition was sufficient for the Hilbert transform to be bounded on LPW. So this is kind of a natural condition. As I said before, the AP hat condition is somewhat natural in that it characterizes martingale BMO and it satisfies a reverse Haldor inequality. And the way we proved the weighted estimates for the commutator in our previous paper was we used this so-called Cauchy integral trick. And you get to a point in that proof where you have to consider a weight that's like a product of weights. So you have to separate a product like e to the delta b, where b is some BMO function, and a weight w. Well, if you want to separate that out, then you have to apply Haldor's inequality. And so if you want to get back to the original weight, you're going to have to apply a reverse Haldor inequality. And this wasn't available in the non-doubling setting. But once we were able to get sparse domination for these special dyadic operators, then we could get around this issue because, like I showed you before, we could just decompose the commutator and iterate the weighted estimates rather than having to separate a product of weights. Okay, and I think that's all I have. So thank you very much.
Oh, let's thank our speaker. Thank you very much for the